Good afternoon, everybody. Today, we're glad to have with us Professor Veronica Dexheimer. Veronica is an expert in nuclear astrophysics. She got her bachelor in 2003 from the Federal University of Rio Grande do Sul. Then she got her master in 2006 from the same university. She got her PhD in 2009 from the Frankfurt Institute for Advanced Studies in Germany. And she worked as an adjunct professor and as a visiting assistant professor at Gettysburg College. She worked also at the Federal University of Santa Catarina as a researcher. And in 2013, she joined Kent State University as assistant professor. And in 2020, she became an associate professor at the same university. Currently, besides being a professor there, she's the director of the Center for Nuclear Research. Professor Veronica is a member of a few collaborations, Muses, NP3M, and Fribe Theory Alliance collaborations, and she appeared among the world top 2% scientists at the Elsevier Data Repository in 2022. So it's a great pleasure to have Veronica talking to us today.
Today I'm going to talk about neutron stars and why do they belong in the phase diagram and why can we do them to learn about dense and high energy matter in general. So most of the work here is done together with people from my research group at the Center for Nuclear Research here in Kent, Ohio. But some of the work was also done with members from the Muses collaboration in other institutions, and also the NP3M institution, collaboration. So I am at Kent, Ohio. I put here in the map for the people that are not familiar with Ohio. Is a large state university. And my group has been researching neutron stars here for about 10 years now. And the reason I think neutron stars are important is because they are the perfect laboratory to study dense matter. And what I mean, different people mean different things. What I think that dense matter is density beyond saturation density. So this is a nice diagram that my postdoc Rajesh Kumar made of a neutron star. And the reason I like this diagram is because sometimes when people are trying to make sketches for neutron stars, it looks like the crust is larger than it is. The crust is actually quite thin. It's very important for observable properties, but it has less than 1 kilometer of radius. So I think this figure puts a little bit more in evidence that most of the neutron star actually is the core, which is defined as a density being larger than saturation density approximately. So dense matter is found in astrophysics not only at very low temperature in the MeV scale, but it can get quite hot. So when neutron stars are forming supernova, they can reach few tens of MeV. So this is the first calculation that was done by the group in Poland and other collaborators across Europe of a supernova explosion with a realistic equation of state that allows the confinement to quark matter. So they made a phase diagram here. And I'm not going to go into details of these. They just went through different trajectories here. This is drawn as a function of saturation density. And what I found is when they allow the confinement to take place, that can make very massive stars successful in producing neutron stars versus black hole. But what I really wanted to show is this plot here on the right that shows the entropy. Supernovae generate all this matter that comes out, but within the radius that's going to become a neutron star here, which is a little bit bigger than 10 kilometers of radius, what's called here the proto-neutron star radius, you can see that after the second shock generated by the confinement, you can get very hot matter. That was my whole point here. But maybe a few tens of MeV is not interesting. but definitely I think everyone has to agree that many tens of MeV is definitely interesting, no matter if you study how high temperature you study. And this can be achieved in neutron star mergers. So this was our calculation, and now I'm together with the numerical relativity group of Luciano Rezala in Frankfurt, and also especially Elias Most, which used to be in his group at the time. We made this first simulation of a neutron star merger, allowing for quark deconfinement with a realistic equation of state. And the only thing I want to discuss here is the temperature that you reach. So mergers are complicated, as supernovae are, and if you try to draw where you are in the phase diagram, everywhere, at all moments in time, it just covers the whole thing. So here we're just showing the largest density in diamonds, and the largest temperature in circles, and the largest temperature jumps at some point from a ring outside the star to the center. But the important thing here is that you can reach about 50 MeV of temperature, and some other simulations with non-relativistic equations, the state can get even to 100, so it can get very hot. So since I think I convinced you that neutron stars belong in the QCD phase diagram, I'm going to discuss a little bit about the phase diagram. This diagram, I think, is different from what most people are used to draw. I didn't put lines here for different phases, but instead I put regions for physics that we understand. And by that, I mean provide quantities such as the equation of state. So this is a mixture of theory and experiments. By theory, I mean first principle theory or effective theories that can be controlled, and lots of different experiments, astrophysical and in the laboratory. This is a two-dimensional phase diagram. I'm going to discuss more dimensions later. So this is a little bit deceiving in my opinion, because first of all, there's a log scale on the bottom, which was necessary to show PQCD in the plot. And also that I'm compacting a lot of dimensions in 2 dimensions. So it might seem like we're covering almost everything, but actually there's a lot of empty space that we cannot describe yet here in the phase diagram. So I'm going to come back to that. And this is a way also to show the importance of effective models, which have, of course, not first principle theories, but they have the advantage of covering this phase diagram. But before that, I wanted to discuss the different regions. We have lattice QCD here in green, perturbative QCD in pink, heavy ion collisions in brown, and you can notice that heavy ion is kind of fuzzy on purpose because there's a lot of debate about exactly where this region covers here. Chiral effective field theory in gray, a bunch of lot of low energy nuclear physics here, including low energy heavy ion collisions in blue, and neutron stars are in the very bottom at 0 temperature. And why only 0 temperature? If I was telling you that we have lots of information we can have lots of information about hot and dense matter. The issue is that we, for example, if we're talking about gravitational waves, we had a very important measurement a few years ago of one gravitational wave that provided the tidal deformability, which is this quantity that's related to the finite size of matter, and it was measured by LIGO and Virgo. But the issue is that this part here that was measured of the neutron star merger corresponds to the part until the merger. The post-merger part was not observed. And the reason for that is because of small amplitude and large frequencies. It is about to be observed, hopefully very soon. And in that case, we have neutron star or astrophysics information here at final temperature, maybe up to 100 MeV. By the way, if you guys have questions, please stop me. So now I'll talk a little bit more about these different regions.
Veronica, can I ask you a question?
Sure, please.
Alejandro Ayala here. The phase diagram you're showing I imagine that contains like boundaries of information. In other words, if you speak about lattice QCD, the lowest part or portion of the region is the boundary of information that we have for temperature and density. Is that correct?
Yes. So let me get to this now.
Okay.
I'll talk in particularly about lattice QCD, which I'm not an expert, by the way, as many things I'm showing here. So this is from an expansion from the group from Houston and collaborators that goes up to a baryon chemical potential over temperature of 3.5, which was a little bit larger than what they had before. And this is provided in mu-B. So my group, I think it was my postdoc project, which work transforming this into baryon density. From that, so this is exactly this boundary here. And within this region, which again is an expansion because we cannot easily do lattice QCD at finite chemical potential, it provides quantities such as the equation of state, also different susceptibilities, partial pressures. I just think it's important to note that the partial pressures assume that you have an ideal resonance gas for the hadronic contribution. It provides quantities such as the pseudo-phase transition line, so I'm not showing lines here. We thought that the regions offer enough debate as it is. Also, which in my opinion is the most important thing, is the limits on the critical point location, which, as far as I know, the most updated calculation provides mu-B larger than a 300, which is again where the critical point is not found in quantities as such as the susceptibilities. And from a more first principle point of view, the temperature is bound to be less than about 130 MeV.
I'm sorry, it's just a question. So, because we are more used to know that the scale, the x-axis in chemical potential. So, which is more or less the equivalent. So for example, one in this scale correspond to which value of chemical potential?
So mu-B has to be larger than 300 MeV for the critical point from lattice. And here we try to translate the whole region we have information. I didn't put a region here for the critical point. So you're asking me what's equivalent to this in baryon density?
Yeah, yes.
Ooh, that's a tough one. I'll have to go back and look at the calculation that my postdoc did to get to this, the right side of the green region here. Because I don't think
we are more used to have the scale in chemical potential, so that's why I'm asking this. No, it's okay. Fine.
I think to make everyone comfortable, I have to have chemical potential for the top part and density for the bottom part, because in the bottom part everything is given in baryon density. So when I'm making this transformations here, but that's a good point. I'll check what that is later.
Okay.
And the reason that we put in this format was especially to try to fit PQCD here, because I got tired of telling my group like, oh, PQCD is here and just wave with my hands, but we wanted to put it here in the shape of some sort of circle. So perturbative QCD nowadays available for 3 next to leading order using Hartarmo loops offers you different quantities from perturbative QCD that can be applied up to 2 times the critical temperature here, the mu-B equal to 0. As far as I know, people don't understand why it agrees with lattice QCD that low in temperature. But in baryon chemical potential here on the bottom side, this extends down to around 40 times saturation density. And this includes several quantities, for example, the equation of state, but also things like the curvature of the QCD phase transition line, which also agrees with lattice QCD. And I just want to, and things like transport coefficients, but I wanted to end the slide saying that although the applicability is at very large densities or temperatures, especially densities here, it can be used to constrain matter at much lower densities, up to a couple of times saturation density, as is done in this reference here. And then I have Carrier effective field theory, also computed up to 3 N3LO for the next to leading order. And this particular order is using 2 body forces with 3 body forces is one last order. But for neutron stars, what the quantity is relevant to us is that this can be used up to 2 times saturation density, and to a temperature of up to around 20-25 MeV. It provides very interesting quantities, not only the equations of state for different kinds of isospin asymmetry, but also provides the symmetry energy itself and its derivatives, which is very important to understand how the stiffness of the equation of state changes when you change isospin. And it can be used all the way up to the liquid gas critical point. And then I stopped talking about theory and talking about experiments a little bit. As a theorist, it's very hard for me, but I will do my best. So these regions here, and as I said before, the heavy ion collision one was particularly debated for a long time until we managed to converge to a region. Heavy ion collisions offer quantities like particle yields, which is the simplest thing you can get, but it's very important. For example, enhancement of strangeness can point to deconfinement. Also, fluctuation observables, such as cumulants, that can be related to thermodynamic susceptibilities, like what I was discussing before in lattice QCD. And this can be used to exclude a critical point in a certain regime. But heavy ion collisions also provide quantities such as flow harmonics and things like HBT, which can be used to trace different particles and their relations. But not all heavy ion collisions are here. We actually bunched the very low energy heavy ion collisions together with this region that we decided to call low energy nuclear physics, that extends all the way up to the critical point of the nuclear liquid gas. This is extremely important for dense matter because we, the theories that provide modeling for neutron stars, calibrate all our models to agree with low energy nuclear physics, especially around saturation. And it's very interesting that although everything is based on saturation, most people don't realize that the errors for measurements for saturation is actually quite large. And that's because these are to some extent model dependent themselves. So this can range all the way from 0.14 to 0.18 or even more Fermi to the -3. And changes in these it can make sizable changes in, for example, the mass and the radius of neutron stars that come out of these models. But other quantities like binding energy still have error. Compressibility, I think, is the biggest one, although most people like to mention this value of 240 MeV. Other works point to values that could be much bigger than that. And also when we're describing neutron stars, because we know that unless there's something very repulsive going on in there, the hyperons will appear at already 2 times saturation density, and maybe the delta baryons appear even earlier. We have to somehow calibrate our models and use these using their potentials at saturation. So I didn't put values here, but there's information about that. Also, the symmetry energy and the symmetry energy derivatives is a function of density. We have experimental values for those. And also, very recently, everyone has been talking about neutron skin measurements from heavy ion collisions, which can be used to estimate quantities such as the radius of neutron stars. And also information about the liquid gas critical point, which can also be calibrated in different models. And finally, I get to astrophysics. Yay. So here we have, I'm not going to say a large, but a number of different measurements that are increasing over time. For a long time, for the longest time, we just had masses, which go from 1 to around 2 times the mass of the sun. But more recently, we start having measurements for radii. It is very interesting that for the ones we have the radii measured by NICE, we also have the mass. And more recently with LIGO, we can also estimate things like tidal deformability. And this is only going to get more accurate very soon with new measurements. And as I said, very soon also expect to extend this pink region here for neutron stars to find a temperature. But so far, I was only talking about the 2-dimensional phase diagram, which we know it's a very simplified way of understanding things. In reality, this is a multi-dimensional phase diagram. I only studied different chemical potentials and magnetic field, which is enough work for me. But people can add other dimensions, for example, things related to vorticity or spin. I think the idea is that in the future, this is just going to have more and more dimensions. So the first ones that I'm going to discuss now are the different chemical potentials. I'm going to include strangeness and isospin and charge, but the quantities I'm going to use are actually fractions and not chemical potentials. Because in my opinion, these dimensionless quantities are easier to discuss. So the relation between isospin and charge is not trivial. And it's not trivial in the case that we have non-zero strangeness. If the strangeness is 0, they just correspond with a 0.5 shift. So if you say you have 0 isospin fraction, you have the same amount of neutrons and protons, for example, your charge fraction is 0.5. But if you have strangeness, you break this. And you also break this relation between your free energy being exactly your baryon chemical potential. You end up with a shift. So your free energy, which is the quantity, which is the same in all different phases, which I show here in the bottom, using the CMF model as an example. So this is the deconfinement region as a function of free energy. And the third dimension that I'm adding here going into the page is the isospin fraction. But if you're looking at baryon chemical potential, instead of the box on the bottom, you have the 2 boxes on the top. And each box has 2 different colors because I'm just showing you here. So the blue regions, I vary the isospin fraction between minus 0.5 and 0. So 0 is isospin symmetric matter. And going to minus 0.5 means having, without strangeness, you're having pure neutron matter. But if you are thinking about charge fraction instead, I'm going from 0 to 0.5. So you see that this shift here is not 0.5. If there was a simple 0.5, these curves will be all overlapping in the whole regions, and they're not. So the overlap increases with temperature, first of all, where you start having more and more strangeness, but they're particularly large in the hadronic side, which is the top left box here. And why is that? Is because they're usually a lot in any model that allows hyperons to be present, they'll be present around the confinement region. For quark matter, this is not the case at 0 temperature because the strange quark is much heavier than the other one, so usually appears later. Although we don't know at which density the confinement appears, we have a rough estimate. We know it's not too low close to saturation, but we know it's not too high to the point that the hadrons have to be overlapping already. So going back here, now we have to add magnetic field. And for this, I started studying a few slices of the phase diagram because, of course, it's complicated to talk into how many dimensions we are? 5 dimensions. So what we do here is we choose to study first just neutron star matter. And by that, I mean matter that is in chemical equilibrium with leptons and charged neutral. So it has very isospin asymmetric or has a very low charge fraction. And at low temperature, it has a bit of strangeness and a lot more net strangeness as you go up in temperature. So here show again for the CMF model, which has a hadronic phase and a quark phase, different magnetic fields. And we studied, this was the PhD work of my student, Jeffrey Peterson, how does the magnetic field affect the confinement. And we saw here that these magnetic fields that we're choosing have a very comparable effect with the temperatures that we're studying. So here on the right, we're studying different temperatures. On the left side, the dashed lines show the effects of anomalous magnetic moment in hadronic matter only. On the right side, the different lines mean different temperatures. And again, as I said, they are comparable, both for neutron star matter. So what we found is that the phase transition gets stronger for larger magnetic field and takes place at larger energy density and baryon chemical potential for the CMF model. We did extensive comparisons. So I spent my last year in Coimbra working with the Portuguese group of Constança Providência and also Pedro. And what we found out was that some of the features were common between the CMF and the PNGL model, which they work with, and some of them were not. And this one was not. One feature that's common is that the phase transition gets weaker and takes place at lower μb for larger temperatures. And the reason that these models do not agree is not surprising. And that's because although the PNGL model has chiral symmetry restoration and deconfinement in a way, it does not present a hadronic phase, while the CMS provides both a quark and a hadronic phase. And actually, hadronic phase is what drives everything because the presence of the hyperons are strongly influenced by both the magnetic field and isospin, and also obviously strangeness. So, yes.
Can I have a question? We have confinement, the confinement transition in PNGL usually at fine temperature, not at fine density, right?
So what they study, what Pedro Costa studies, for example, is they calculate phase diagram of T and μb and calculate when you change the magnetic field, the position of the confinement. They do both, T and μb.
Okay, this cannot be done for zero temperature, for fine temperature, right? To include the confinement.
Because you're saying because of the Polyakov loop?
Yeah.
Yeah, so in that case, the Polyakov loop has no influence. It's just like an NGL equal to 0.
Okay. So the comparison with CMF was done at fine temperature.
And 0 temperature too. So it went all the way down. But then it's just an NGL model.
Okay.
So yeah, so in that case, the phase transition, but in both models, chiral symmetry and the confinement are related. They're not independent. It could be made independent, I guess, but it's not. So now we're trying to add another axis in a very simple way by switching to heavy ion collision matter, which means here 0 net strangeness and isospin symmetric. And again, we're looking at different colors for different magnetic fields and different styles of line for different temperatures. And I added in brown and gray, the results from the previous plot. So I think the most important here to notice is that temperature, magnetic fields, and different kinds of matter, meaning isospin or charge and strangeness, they all have comparable effects. I know it's complicated to try to draw conclusions here because there are 1,000 lines, but the message here is that phase transition takes place at larger μb and is stronger for heavy ion collision matter in the CMF model. And again, I wrote CMF model because the PNGL we found different and kind of opposite effects. And again, it's because in the CMF model, everything is kind of drawn by the hyperons. And if you go from neutron star to heavy ion collision matter, because we now are not allowing for net strangeness, especially at lower temperatures, the hyperons just disappear. So I'm not going to talk for much longer here because I'm sorry I started late. But we can also study the different kinds of matter in simulations, because so far I was just talking about the equation of state itself. And we did that using a version of the CMF model, which is not the version I was studying to discuss the previous plots. These are a more suitable version that also includes a lot of thermal mesons, and this is better suited for larger temperatures, like the ones that you can achieve in very high energy heavy ion collisions. And this equation of state was provided by Jan Steinheimer from Frankfurt. And you use this in two different codes, both relativistic hydrodynamics codes, one for mergers, which also contains general relativity, of course, from Luciano Rizzola, and one for heavy ion collisions, which is the Frankfurt-Shasta code. This was run by Anton Motornenko and the other collaborators from Frankfurt. And so we're running the same equation of state, just changing conditions related to strangeness and isospin. And we're focusing here on trying to find which masses of stars we have to merge to match laboratory conditions that people are studying in Hades. And the reason for that is because those are the ones that produce comparable densities. If you go very high in energy, we also go very high in temperature, but then low in density. And you want it as large as we can in density to compare with mergers. So here is a double neutron star merger, and a gold-gold heavy ion collision. And we're just looking at, first, we're looking at geometry. So here, just looking at obviously very different sizes, they differ by about 18 orders of magnitude, but they have similar geometries. Nothing static here, right? So I had to take a few snapshots. Also look at different time evolution. So here we have to reduce in the x-axis to 1 dimension, these collisions that were not 1 dimension. So I have to integrate over just to get a rough idea. And in the y-axis here we had time. And this is showing how different entropies and temperatures, entropy on the right, temperature on the left, are achieved over time. And in a sense, please nobody get offended here, the heavy ion collision is a simpler system because it's expanding into vacuum. These are ideal hydro simulations. So unless you have shocks here, the entropy is conserved. But on the left is a much more complicated system to describe. And the reason for that is gravity. And I think this is going to become more obvious in the next slide. Just my last one, by the way. And here we put both of these simulations or collisions, if you want to put in that way, in the phase diagram. So we have just baryon density on the x-axis. We're not showing all the dimensions. And you have temperature in the y-axis. On the left, you have mergers. On the right, you have collisions. And the goal was to try to link what's happening on the right with what's happened on the left. So these are a few energies that we were told, I was told, that correspond to the energies that are exploring in GSI in Hades. And that correspond to entropies on the top case, more towards 1.8, on the bottom case, more energetic towards 2.2. And on the left, we're trying to match these to different masses for mergers. So here on the top, we're merging 1.3 solar mass, on the bottom are 1.4 solar mass, which is more or less what LIGO measured in that merger that I discussed before. If more massive stars merge, it happens too fast, and it's hard to see it before it collapses to a black hole. Very early, very low mass ones don't produce interesting results in temperature that you want to be able to compare with the collisions and density and everything. So what we found is that lower masses around 2.6 total will produce a stronger line here around 1.8 entropy per barium. And the color code here, it's something that Dexheimer came up with, which is amount. So a very bright color, this means that there's a lot of matter spending a lot of time having this particular temperature or density. And that's what the color code means here. And when you use more massive stars, here on the bottom, you have more matter having entropy around 2.2. And of course, probably you're thinking, oh my God, Veronica is crazy. Why is she showing this, this merger here on the left that has different regions? Well, those regions we cannot get rid of because of gravity. So the initial stars, when they merge, they produce this hot ring that I didn't go into detail, but this hot ring that produces has low density and large temperatures. And that's here what you see on the middle left of the left panels. And that's due to the gravity, to the remaining gravity, or the remaining effects of the gravitational field of the original stars. And this very cold and dense region that you form here on the bottom right of the left diagrams is the hypermassive star that you form that has a very dense core. So again, this is due to gravity of this hypermassive neutron star you're forming. And you have to ignore those parts because if you want to compare to a collision, you want to exactly not pay attention to gravity, but we have to pay attention to something that allows this comparison. And in our opinion, something that you can use is the similar trajectories for entropy here. So I get to my conclusions. So neutron stars are interesting in my opinion because they allow us to access this different location of the phase diagram that's highly strange and isospin asymmetric. And with neutron stars, we're going to be able to extend this to final temperature too. I think magnetic fields are very interesting. I dedicate a lot of my time studying them. I didn't show you here, but we have a lot of, my student Jeffrey spent a lot of time studying magnetic fields. Not they're just constant, those are the ones I show you today, but also following specific profiles for astrophysics, because you can calculate what's the magnetic field that we expect inside stars, but of course it's more complicated because it depends on the direction. We haven't studied these in mergers yet. In mergers, we can produce strong magnetic fields, but so far people have done is merge normal stars. I mean, neutron stars have very strong magnetic field to begin with, but merge normal neutron stars magnetic field, for example, 10 to the 10 Gauss, and then you produce magnetic fields around 10 to the 16, maybe 17 in a merger. But what I'm working right now with Elias Most is study mergers of magnetars, which already have magnetic fields, starting at the surface at 10 to the 15 and being higher inside, and see what kind of interesting physics we can find in the extremely high magnetic fields that the stars are produced when they merge. And unfortunately, today I could only show you slices of phase diagrams, and that's because this is extremely computational intensive. For us to have one run of density at a fixed temperature magnetic field takes a long time. So to produce what we wanted, which is 5-dimensional phase diagrams, this will take forever. So now we're working together with many collaborators in the MUSES collaboration, which is, for the astrophysicists here in the room, something that in some ways resembles Compose, which is a repository for equations of state, but this one is different in a few ways. So first of all, we're going to have different modules for different first principle theories like lattice QCD that's going to be merged as the user wishes with models like the CMF of chiroeffective field theory and unified in different ways that will be selected by the user, and is being developed with lots of different physicists and computer scientists as we speak. So these collaborations between Kent State, the University of Illinois Urbana-Champaign, and the University of Houston, but you also have senior investigators and collaborators around the world, including Mateos, which I think is a part of this group here. And that's all I had. So sorry I was late, but please ask questions.
Thank you very much for the nice talk. A lot of new information for me. So let's now open for more questions. Christian, go ahead.
Yeah, I don't know how to raise this
hand. Yeah, no, you did fine. Go ahead.
Okay, thank you very much for the talk. Those simulations are made, if I understand, with this CF effective field theory model. Yes, this is the CS for conformal. What is?
Okay, so sorry, I didn't talk about the model, but that's because it would be a whole talk by itself. So I don't like to use it's a Cairo model in the same way as the NGL is. I don't have a slide about the model, shame on me. But I don't like to call it theory because it's not an effective field theory in a way that is not a controlled expansion. It's an effective model in the other meaning for the word effective, which is a model we just calibrate to work on a specific regime of energies. So what we do is we start from Cairo symmetry rules, and we build a Lagrangian. And from that, we can derive all our quantities, thermodynamical quantities.
But this is something like a model?
It's not. So if you think about, it's a Cairo model. So if you think about the simplest Cairo model you can have, which is the linear sigma model, is a slightly different because a non-linear realization of the sigma model. It's different from the NGL in several ways, and in my opinion, it's much simpler, especially when you want to do things like include magnetic fields. But for example, in the Veronica model, you still exchange the interactions between the baryons are still done through interactions with the scalar vector mesons. But I feel like I want to draw somewhere, but I can't. But for example, instead of the masses being just modified by the scalar mesons, here they are generated by the scalar mesons, and the masses go down to zero at very large energies. So the mass is being created, not modified by the medium.
Yeah, but in the same way with the condensation of bosonic resonances, is something like hadrons coupled with bosons that you use in field theory and yeah, also okay, it's something similar.
Yeah, so do field approximation.
Okay, and you include also hyperons and
yes, and we include quarks in a similar way, so that I'll do a comparison of the NGL model, which was originally made to be a hadronic model, was later applied for quarks. So here we do sort of the same thing inspired by it. We use the same model to describe the hadrons as a model to describe the quarks, which is the same kind of interactions.
Okay, so the quarks interact in this model. You also have interaction with quarks.
Yeah.
And you calculate the quark sector of the pressure and the hadron sector of the pressure, so in chemical equilibrium, and then that's how you set the phase transition.
Yeah, so we are not putting two different models together. We allow all degrees of freedom to exist at the same time. So at low temperatures, you have just hadrons or just quarks, but at large temperatures, they allow to coexist. So we can describe also the critical point and the crossover at very large temperatures.
Okay.
So they can be either favor or unfavor, but at very large temperatures, you end up with everyone there. And they're all interacting with this mean field of mesons, which interact back with them.
Okay, see.
So it's an effective description, but I don't like to use the word effective, not to mix it up with things like our effective field theory.
Yes.
Okay.
So just last question. So the coupling with quarks is just an effective parameter that you fit at some point.
Yes. So we have a potential for our deconfining parameter phi, which was inspired by the one from the PNGL model.
Okay, you minimize the potential. Okay. Okay, thanks.
Okay, so let me just take a ride in Christian's question before going to Diana's question. So do you consider when you include magnetic field, do you consider in this model the coupling depending on B? Because from NGL to fit lattice, we know that this is necessary to reproduce lattice results. So do you do this here too, or?
So nothing is changing when you add the magnetic field. We have anomalous magnetic moment for the hadrons only and the leptons when you include them. But I know that there's a lot of debate on, for example, how the anomalous magnetic moment will change with the strength of the magnetic field for the quarks, but we do not include it for the quarks.
Okay.
So no.
Yeah, maybe it's something to think about. Okay, Diana. Diana, you raised your hand, right? Hello.
Can I stop sharing so I can see your faces? There you are.
Okay. People, you can turn your cameras on. Diana, are you there? Okay. I don't know. So more questions? I do have more questions, but let's see if... okay, so you're here. Okay. Go ahead, Diana.
Sorry, my computer is crashing all the time here. Can you hear me?
Yeah.
Yes.
Okay. First, thank you, Veronica, for the very nice talk. And when you mentioned that you can have a coexistence region, how do you guarantee that the Pauli principle is not being violated when you have quarks and nucleons or hadrons?
So this is done species by. I think you're thinking about something much more complicated than what I'm thinking about, because I know your work. But in this simple setup that I study, this is counted simply because it's considered species by species. So I just have to make sure in my formalism that for each set of quantum numbers, I only have one particle in one state.
I see.
But I know that you do something much more complicated because of quark-ionic matter, right?
Yes, this is why I'm asking, because if you have this possibility for the existence of coexistence phases, maybe it's possible to apply in this context.
Yes, and I discussed two different versions of the CMF. I know that's not exactly answering your question, slightly different, but in one of them, we also give a finite size for the hadrons.
Mm-hmm. I see.
In the other one, we don't.
Okay. Okay. Oh, but that's it. Thank you.
May I have a question? May I have a question?
Go ahead.
Yeah. It's still not clear to me which are the basic degrees of freedom of your model. I mean, are quarks or hadrons or both?
So we have the work I discussed today. When I discuss the CMF model, we have electrons, muons, and then you have the octet of baryons and the 3 light quarks. And then the interactions happen through a mean field of mesons, which are scalar vector, isoscalar as a vector, and some have hidden strangeness.
Okay,
but
so you have quarks and hadrons at the same time. Or
yes, and in one of the prescriptions from the CMF that I presented, we also have free thermal mesons. The whole PDG, as far as I'm aware, but they're free.
And in the calculation, you mentioned that number was used.
Oh, okay. So the ones that I didn't show, but I discussed for comparison, the ones provided by Pedro Costa had the 3 light quarks.
But they only have quarks, or you have hadrons?
No, I had quarks. So the lines that we're comparing in that sense, you know, I'm not sure it's a great comparison that we did, but it's just hard to find models available that provide equational state, including magnetic fields, and has the deconfinement line of a critical point. So the more a way to get rid of the model dependence is by comparing different models, but for that we need more models with magnetic fields. So that's work in progress from everyone's side.
More questions? Or are you done, Norberto? Sorry.
Just a comment about your question, Anna.
Okay.
I guess that the dependence on the coupling constant is probably needed for larger magnetic fields. I think she's working with rather small magnetic fields. I mean, large.
No, my magnetic fields are large.
Yeah, but for our scales, it's small. I mean, it's around the biomass square.
Yeah, power mass and up.
So it's around 1 biomass square.
I see.
I guess for that magnetic field,
then it doesn't make much difference, right?
Yeah. This is my feeling. Maybe
okay.
I can.
I have the same feeling. Yes.
Yeah.
Okay. So what's the value that I have to watch for?
Yeah, usually when we talk about the magnetic field dependence of the coupling constant, we are talking about, say,
1 GeV squared.
Okay, that's large.
Or half GeV square, let's say half a GeV square, which is probably something like, I don't know, 5 or 6 times 10 pi squared.
Yeah,
or even more.
This field that Veronica is talking about in our scale is less than 0.1 GeV square.
Yeah. For us, it's small, small magnetic field.
I see.
Kind of funny, but
I see. And for the values that you expect to have and the core of neutron star, because what do you expect? I mean, like 10 times higher or 100 times higher? I heard 10 times, but I want to ask you because I have the impression that this is not established, right?
So we don't know exactly what the magnetic field is inside a neutron star. But the problem is that when you go too much above 10 to the 18 Gauss, for sure when you approach 10 to the 19 Gauss, your stars start becoming a donut. And that the numerical codes cannot deal with it, but just from an intuitive point of view, that also makes no sense. Okay. So at large magnetic fields, the central density of the star is not the center anymore, but sometimes it really becomes a donut. So we know that that's not the case. The problem is until recently, the only way using full GR to describe a neutron star was choosing a specific configuration for the magnetic field. It had to be either poloidal or toroidal, but we know that to have a long-term stability in the star, you have to combine both. And only very recently, there was a paper from Shapiro combining both in a full GR approach. But so far, they only have simple polytropic equations of state as input. So, this is a field that's still developing, understanding exactly what's the magnetic field configurations and using realistic equations of state so you can estimate what is center one, but it's not 10 to the 19 Gauss for sure. And also even 10 to the 18 Gauss, you are not going to have that on the surface because we understand that that will create all sorts of crazy physics that we do not observe. So on the surface is smaller and then increase up to something maybe two orders of magnitude inside the star. So it's not as strong as the fields that you guys discussed.
Mm-hmm. Yeah, then this is something you don't have to care about, like the dependence and the, I see. Okay, thank you. Just more questions?
I have one. Veronica, usually in an NGL model, we do not have an isotropy on the pressures for this magnitude of magnetic fields. In this CMF model, do you have an isotropy?
An isotropy, you mean the one caused by the magnetization?
Yeah, I'm seeing if the perpendicular pressure is different than the parallel one, let's say.
Yeah, so this one, the paper that I compare from the NGL model, they didn't provide that, but it can be calculated. Can even calculated numerically, taking the derivative of the PdB, we can calculate the magnetization, then use that to calculate the anisotropy. You just need a two-dimensional table. The problem is that once you go to finite temperature, it becomes very computationally intensive to create two-dimensional tables because the codes get very slow with temperature. But in principle, something you could calculate.
Yeah, because in NGL, there is nothing in this magnitude of fields. They are very similar.
I think the group from Deborah has provided those in papers.
Yeah, in NGL, there is no anisotropy if you do the calculation. But I was curious about your model.
Sorry, why is there no anisotropy?
Because the magnetization is very slow.
Okay, it's small. I don't think in my calculations would be larger because I think they should respond more or less the same way to the magnetic field. I'm just guessing here, but I think it should be comparable. But that's a good point. I should take a look at some plots and see
Thanks.
if they're comparable. I myself have never done star calculations with with magnetic field and MJL. But you have, right, Ricardo?
Yeah, we have done this.
So you have them.
I was just curious in a CMF model with these more degrees of freedom, if you have some difference.
I don't think the magnetization amplitude will be different. I think most of the difference is when you change strangeness and isospin. Then everything is different because of the hyperons.
Okay.
But the quarks feel more the magnetic field, right? Because they're lighter. No.
Okay, so are you done, Ricardo?
Yeah, thank you. There is another raising hand.
Okay, Manuel?
Hi, Veronica.
Oi.
Nice to see you. The first thing for us is that to know that 1 GeV square is 5 times 10 to 19, because you use some numbers that are for your scales, but not from neutron star scales. So what I know is that when the magnetic energy, B square over 8 pi, is at the order, or magnetic field is at the order of 10 to 18 Gauss, okay? So the energy is 10 to 36 because it's B squared, dynas per centimeter squared. So in that case, magnetic energy and pressure, okay, it's comparable to the magnetic and to the energy density and pressure of the star. So in that case, you have an isotropy. And an isotropy comes not only by the magnetization, but really because the energy momentum tensor in the z direction is not equal to the perpendicular direction. They have a minus sign, okay, for the energy density. One is positive b squared over 8 pi, and the other is minus b squared over 8 pi. And so that's the scale. It's 10 to 18 for us, neutron stars. But for you, I don't know, if you talk about 10 to 9, because what you, to see, if you have an isotropy, is to see what is the energy, density, and pressure of your model of your matter, okay, quark matter. So, and compare with b squared over 8 pi, and you find your b, where you are going to have an isotropy. I don't know if I make me clear.
No, you are. And in the paper, we show the different pressures. I just didn't show here today.
Yeah, but I'm saying for Ricardo, to have an isotropy, your b needs to be square root of p or rho. Okay, that's it. If it's lower, your pressure from the magnetic field is not going to change anything on your method. Okay, so I don't know what are the. Seems that you are using 0.1. Is that 0.1 GV squared? Is what your is the scale for?
No, it's
method?
much higher than this.
I started 10 to the 18 Gauss, which is
Yeah, for us it's 0.1. For us it's
pi
0.1
square.
GV squared.
Oh,
No,
yes.
but for us
When we see an isotropy model, it's for much higher.
Yeah, inside neutron stars, above 10 to 18, as you said, Veronica, you are going to have holes, donuts. I don't believe in that structure, but okay. But anyway, it's too high. Seems to be too high already, no?
Well,
but I don't know.
That's what I said. So we don't know what's in the center of neutron stars, but if emerged stars already have a strong magnetic field, then we expect it to be very high.
Yeah, but
very interesting.
Yeah, 10 to 18, but I don't think more. But okay, if not, the star blows up. No, no, star blows up because the pressure of the magnetic field is positive, so it blows up the star. No, but okay, but at least that was only to say that this exists also for charged stars. The energy momentum tensor is not symmetric. Okay, the R direction is different from the perpendicular direction for electric fields, and for magnetic fields is the Z direction of the energy momentum tensor. The pressure, let's put on Z direction, is different from the perpendicular, from the structure of the energy momentum tensor of the Maxwell equations. You know? But okay, but I think it's these questions of mergers now are very, very interesting, and even I don't know that have people talking. I didn't follow all your talk because I need to go out in between, but exists now one very long period star that irradiates in radio, that they are thinking that it has 10 to 17 Gauss, of course, if P dot is correct, but so maybe this 10 to 15 Gauss of magnetars has been, I don't know, maybe you have already something higher, I don't know, but are new things, new sources that have appeared now that emitting radio with long periods, okay, that maybe you are aware. I don't know.
I'm not sure I know this reference. Can you send me just so I can check if it's the one I already know or not?
There are two sources that have periods of 20 minutes. Okay, so it's much larger than neutron star, but can be a neutron star that show radio emission that is difficult to explain, but it's quite interesting because should be understood. No? Okay.
Please send.
I will send you. Yes, a lot, several of. All them from last year and this year. No, I will. So okay, that's it. Okay, so, thanks for the space, the time.
More questions? I have one last question that I don't want to miss the opportunity to ask. So it's in the beginning of your talk, when you talk, you're in this lattice collaboration, right, with the Houston group. So this Taylor expansion, how is it the convergence of the expansion? Do you have control over it, or?
So I see them presenting two different expansions, and they use some, I don't know if I can call it a trick, which is some rescaling of things that allow the curves to end up on the top of each other. So they have some different rescaling. And one of them is the one that I showed that allows them to expand to 3.5. The older one, I think, was 2. So that's not a normal expansion like other groups had. But I think some of the things that I was discussing that I think are very interesting do not rely on the expansion scheme, which is, for example, the maximum temperature for the critical point. That does not rely on this expansion, because I know some people are reluctant about those.
If I may ask or comment on that, maybe this is the meaning of your question, Anna. The point is that perhaps Taylor expansion, because at the end this is a Taylor expansion as far as I understand, may not capture or not be able to capture criticality. Because see, this is exactly the point. Near criticality, the expansion is not analytical of observables. So is this the sense of the meaning of your question, Anna? Yeah. I also have this question. I'm always curious about this bound set by lattice, because see, in principle, these expansions may not be valid near criticality.
So the one that they offer is the chemical potential for the critical point comes from this expansion. They claim that they can capture the criticality, but don't ask me about details.
Right. No. I think this is what Anna meant, and I just wanted to clarify.
Okay. So I thank you very much again for the talk. I will stop recording now.